I will be giving examples for a few things today. One is this one. This is what we call the stabilization. Nothing works today. Okay, this is what we call the stabilization loop, right? This is stabilization. So this architecture we use for stabilization, right? And we have another architecture, told you about, a plus minus, x dot equals ax plus bu, and x. And instead of putting the k over here, we put the feedback gain k over here. Plus, minus. You add it over here. So you take that x and it goes over here, and this would be an x command. But this is not always applicable, of course, because the x and the x command must match in size, and that's not always possible, right? And the x command, the x and the u, they all have to be kind of match in terms of size. That doesn't work. Here, that's not really, here they don't have to match, because I can simply have any matrix k over here, and we have seen that even if you have only one input, you might have multiple states, and you can multiply them with k and send them over here. This is, of course, not possible in this case. So what we usually do in these controllers is the following. We take that, okay, take that, so it'd be nice to have, let's see if they work. All right, that's better. So we just take that, okay, and then we would wrap another loop around this, okay, around the stabilization loop, to track something, to track a variable, okay? So this is the stabilization, and this would be some sort of a tracking problem. Tracking problem. The reason I'm calling this a tracking problem is this signal over here is xc minus x, so it's kind of the error, right? So you're trying to reduce the error. If there's an error, you multiply it with k and send it over here. But this is not always possible, so what you would do is you would simply take this, okay, take one of those variables and wrap another loop around this, okay, plus minus, and this would just simply go over here, okay? This would be a tracking problem. So what you have now is you have this control, this closed loop system, okay, which is actually, again, x dot is equal to a minus bk plus bu, right? That dotted line is that. So this is another closed loop system, so you could call this one a prime, okay? So it would be like this. X dot is equal to a prime times x plus bu. That would represent the closed loop system. Take one of the variables, say y, and design what we call a tracking controller. So in that case, this would be y command, and this would be y, and this would be error is equal to yc minus y, okay? So this would be like a controller within another controller. So therefore, this one we might call it an inner loop, and this And this one, this that comes out of this, we would call this the outer loop. Okay? Because you would have two loops within inside, one after another. Okay? So this would be a tracking controller. Tracking, we would be tracking a y. In other words, if the error is equal to 0, the input to this would be, if this is equal to that, the error would be 0, then 0 times k, u would be 0, which would be the steady state. I mean the equilibrium point. But that doesn't have to be. If yc is not equal to y, it would immediately respond to that. So we had a similar architecture for this. We called this the integral controller, right? So it would look like this. We had a command plus minus, and then we took the error, took the integral, multiplied it with a k, and then send it to this. X dot equals a prime x plus bu times c times y. Okay? So it will look like that. And this would, the output would be x here. And this a prime still represents this inner loop. Okay? This is still a tracking problem. Tracking with integral. Integral control. So the difference between this and this is the integral over here, of course. So what would it be, why would it be different in practice? In practice, it would simply be different because if you had a yc command, right, the response would probably look something like that. If you design it right, of course. And you would, at the end, have 0 steady state. Okay? This is sort of different over here. You would do the same. You could do the same thing in the tracking problem. You would have time on the axis, time over here, and here you might have y. And here you have yc. And in that case, in this case, you might actually be seeing something like that, but at the end, you might end up actually with a steady state error. So, of course, you might say, why would anybody use this when you can use the integral controller without the steady state? Well, the reason is when you have an integral, you have to be careful. The integral has to start somewhere, right? It has to an initial condition. And if the error keeps growing for some reason because of a measurement error or something, this number here, since you're integrating, might diverge very quickly if the measurement here is not correct or something. So from a practical point of view, the integral is always kind of troublesome, okay, in real life when you start using. That doesn't mean that we don't use integral, we use it all the time, but it's a little bit more troublesome. So a lot of people just add a k over here, and if you design this right and if it works, you wouldn't bother with an integral controller typically, all right? But you might use the integral controller as well. So this is kind of what I want to do. Do you understand all of this? Or you have any questions? I mean, this is what we have done this whole time. We have been calculating k. We have been placing the k value in terms of eigenvalues. We calculated the k using LQR, right? And then this would just stabilize the system, which is typically unstable. What happens in real life, of course, you replace this x dot equals ax plus bu with the real plant. This is now the aircraft. Okay? So you don't have the linear model, it's the full aircraft. So which means that your controller will only work at the design point, which is the linearized point at the equilibrium point and so on and so forth. And if you are going far away from the equilibrium point, it will still work as long as the system is sort of linear. If you lose the linearity and you get a lot of non-linearity, then it will not work anymore. So what do you need to do? You need to redesign controllers at different operating points, basically. Okay? So these are the architectures I would like to show you. And the way I will start here is with, I'm going to show this, of course, in MATLAB Simulink. So let me, okay, good. So I will start with this example here. This is the example I would like to use. So this is the lateral dynamics of the 747. So we have 4 states. Okay, V dot, P dot, R dot, and Phi dot. So I'm expecting that you would find something like this for your project. Okay, it can be an 8x8. It doesn't have to be a 4x4 like this, but you have to somehow, not those dots, of course. You find something like that. So this is the these are the states, and the control U is this is a single input system with the aileron as the control. So this would be the only control. So okay. So this is here the A matrix, and this is the B matrix. In this case, it's a vector. All right. So I'm going to use this example to demonstrate some of these things. Okay. As I said, you could have a system that's not 4x4. It could be larger. This is only the lateral dynamics. And I think this is good enough for me to demonstrate what I want to show you. Okay. I think you did this in your homework, right? You had this in your homework. Okay, good. So I already set up some of these things. What you're seeing here, let me do it this way. I can maximize this. And if I can choose, I would like to bring everything a bit down here. So we have more space here. Okay. And I'll take that. Oops. All that stuff over here. So, and this is my pure dynamics without anything. Okay, so this doesn't look too bad now. Oh, I'm in the wrong place. Okay. So, this is the open loop. Oops. All right. So I think I've shown you how to bring these, how to set up something like this, right? In one of these lectures, I did that. So this is the state space representation. So if you look at this, this is the A matrix. Okay. So let me just copy this just to make sure and say A is equal to that. So this is your A matrix. So let me just clear this up. This is the A matrix, okay? This is the same as this one. Okay? So how did I do? I did write this before into that thing here, into the A matrix of that linear system of the state space representation. So just so we know what they are, copy B. Let me write this as the B matrix. So this is your B matrix. So A is equal to that, B is equal to this. And C, let's look at C is here. Okay, copy. C is equal to that. And this is the C matrix. So what you need to do if you want to set up this this Simulink block, you simply have to write down the A matrix over here, the B over here, C over here, and D matrix is 0 in this case. Okay, initial condition starts from 0. Don't worry about the tolerance and the names and you can write names if you want to, but the tolerances and all that. So this is your model now, okay? So the step input, let's see what I did here. At time 1 second, I want to give a final value of 0.2 to the controls, del A, right? And let's see what that was. That is del A. I don't remember if it was radians or degrees. Do you remember that? It was probably radians. Okay, so from 0 to 0.2. Okay? And how long is the simulation? It's 30 seconds. So when we run this, we should see the response, all 4 states over here. And the first one is the velocity, the side velocity v. And the last one is the angle phi. So that's what we need to see here now. Okay? So this is done. For 30 seconds I did run it. And this is what we have. Of course, you can't really say now which one is which. You have 4 lines here, and each of them belong to each of them belong to one of the states, but we don't know which one is which. So I would just come here and see what is the velocity. So this is the side velocity. It's probably feet per second. Okay? This is the side velocity. The fourth one here would be the angle. 30 degrees. Right? You're rotating. So for 30 seconds, you're rotating quite a bit. All right? So if you reduce this to 0.1, run this again, so you have another step input. The roll changes a lot, much less, of course, to this number. Okay, so this is open loop. So let's go to the LQR, or the feedback controller. The feedback controller would look like this. Okay, we try to move the rest again a bit more. Down here. Down here. Okay. So we have more space. Okay, so now this is the LQR, right? Let me remove this one. Okay, so this is your feedback controller now. We have done that, right? It looks like K times U meaning whatever comes into that thing. You're multiplying that vector with a matrix K. That's what it means. Okay. So this goes through that, and this is the same controller. Okay, so we have to calculate this K now. All right, there's a K over here. The gain is K, so we have to calculate a gain K. So we can do this in a number of ways. We have learned a number of ways to do that, right? One of the ways is the place command, right? We had the place command. For that, we need to specify the eigenvalues where we want to set the eigenvalues to. For example, I already set up some eigenvalues here. I want to move the eigenvalues to minus 0.1, 0.2, 0.3, 0.4. I just made them up. We can also look at the eigenvalues of the A matrix. So the eigenvalues of the A matrix are here. Minus 0.5, minus 0.03, minus 0.003. Okay? If you want, we can just do this. P1 is equal to, place it maybe on a better place. Let's make it minus 1, minus 2. I think it has to be a vector. Minus 3 and minus 3.5. All right, I'm just making this up right now. Okay, so these are the eigenvalues. I want to place the eigenvalues of the closed loop system, and I simply say place A, B, P1. P1 is the vector that contains the eigenvalues. where I want to place the eigenvalues of the closed loop system. I know A and B, it's already in MATLAB, and P1 is that. So if I say that, I should get some feedback gains. So these are your feedback gains. 0.04, minus 12, 78, minus 10. Okay? So go back to that. So because MATLAB and Simulink are connected, it will immediately use that K value as the gain over here. Okay? So if I run this, I should see a more stabilized system. Let's say what the step input was. The step input is again at 0.2. Okay? And I say run. And these are your states. You see, everything looks stable. You have, I remember this is the velocity, so the velocity goes up to 1 feet per second and actually goes down. It's almost nothing. Okay? Look at the velocity, look at the phi. Doesn't even move. You see? But on the other hand, you go up here. I mean, both of them are running at the same time when I hit run. You understand that, right? So you look up here. Oh, the step input here, we changed it to 0.2. 0.2. Okay. Run. Boom. So this is what happens when you have 0.2. See, it goes up to 50, goes down to minus 50, minus 100, minus 250. So it goes on and on. So these numbers here on the, you can see it over there. Okay. These numbers here might not be realistic in real life. So an aircraft might not have this high sight velocity. It might be dangerous for the aircraft. But for a linear model, you can have everything. Because it's a linear model, right? It goes to infinity. I tried to explain it to you at some point. I mean, remember the CL alpha graph, for example. CL alpha, okay? If you just use a linear model over here, you can just use CL alpha times alpha. And that is equal to CL, right? That's something, this is what we use sometimes to calculate alpha, CL. CL times alpha is equal to alpha. What is alpha is 1000. What do you get? You get a very large CL. Is it realistic? Of course not. In real life, the nonlinear model does this. This is nonlinear. Okay? But a linear model means this. Goes to infinity. So which means if you have alpha 1 million, you will get a CL, which is another 10 million maybe. It's physically not possible. But because it's a linear model, you will see that. So I'm using a linear model here, and you get all these large numbers, which might not mean anything in real life, but we have to be aware of this. Okay? So to give you an example, I could use a step input, a final value for the step input, not 0.2, but 1000, actually 10,000 now. Let's make it 1000. Okay. It's still going to run. Still going to run because it's a linear model. It goes 10 to the power 5, you see? So it will still run. In real life, of course, it's meaningless. Okay? But because it's a linear model, you will get a result. Okay? So let's keep it at 0.2. So this is what it looks like, 0.2 input. And the stabilized loop here, this is what it looks like for the stabilized loop. It goes only up to 1. Okay? So if I place these values, if I use P1, let me do this. If I use P1 a lot smaller, let's say 0.1, 0.-2, 0.-3, and maybe 0.35. So I reduced everything by 10. Let's say place. The result will be a lot looser. You know, it loses a lot. It's not really helping a lot. Okay, so that's not good. So another thing we can do now is we can try to use LQR. Okay, we can try to use LQR, and we know the command for LQR, so we can do that. Okay. For LQR, help LQR, we know A and B, now we need Q and R. We know N, I think from last time, I think N, I put 0 for that that cross weight, I would call. But we need the matrices. So I should already have some matrices in memory that I had done like that. So do we like that or not? Let's think about this. The first weight is Q, belongs to that in the LQR problem. So it will do this, right? It will do V, P, R, phi times my Q matrix, it's this one here, and V, P, R, phi. Okay? So I told you, I mean, there are many ways to design this matrix, but what I typically do is, at the beginning, this is probably the best, just select 4 numbers over here, and the rest will be 0. So this is what I did over here, 0, 0, 0, 0, 0, 0. Okay? So what are we going to use for these numbers? First of all, this is a velocity. So it's either feet per second, meters per second. In this case, I believe it's feet per second. Okay? So this is the velocity. P is angular rate. Maybe we can look at the actual just give me 1 second. I want to check the units just to make sure that we have the right units. I should have it somewhere. Well, interestingly, it seems like, oh, here it is. No, that's not true. But I had it in your homework, right? We had the longitudinal one. That was your homework. So it should be the same then. Should be the same. We had this. This was the lateral. So it is then the velocity is feet per second. Okay. This is radians per second. This is radians per second, and this is radians then. So we had actually, and this is radians per second. So everything is radians. So which means when we had 30 radians, this was a lot of turning then. It wasn't 30 degrees, I'm sorry. So the aircraft was turning a lot when I did the open loop. Okay? So we were giving actually quite a high input then. 0.2 is quite large, right? So it is radians. So coming back to this is feet per second. Radians, radians, radians. So how should we balance them in the problem? I mean, first of all, this should be the smallest, right? Because it's feet per second, so it will be a large number. So let's start with 0.01, I would say. Compared to radians, feet per second is a very large number. So one way you can do this, you can decide, you can say, what is the largest P I will encounter during my maneuver? You might think of that. Okay? And then divide it by that. And then you might say, what is the largest velocity I will encounter during the sideways, when I go sideways? Divide it by that. So you kind of normalize. Okay? And then you add these numbers, start with these numbers. What I'm trying to say is that if you want to put equal importance to all 4 variables, you first have to make sure that they are comparable in terms of units over here, because it's a numeric problem, and the numeric problem doesn't know about your units, right? It doesn't know about your units at all. So it's just a numeric problem. So you first of all have to somewhat normalize these numbers when you write them over here, even if you want to give equal importance to all of them. See what I'm saying? Let's say, for example, just to give you an example, let's say the p-value, the roll rate, is maximum 30 degrees per second, right? That makes sense, about 30 degrees. So in 3 seconds, you're already 90 degrees. So that would be a very high roll rate for an airplane like this. Okay? So let's say the maximum is 30 degrees per second. 30 degrees per second. And let's say the largest sight velocity you will encounter would be, I don't know, let's say it's something like 100 knots. Okay, it's 100 knots. So then I would just compare them in terms of this. Okay. Of course, this is now not in knots. This is in feet per second. Let's make it, I don't know. Let's do it 100 feet per second, just to give it an example, right? 100 feet per second. And let's make this one. How many radians are 30 degrees? 0.5. Okay. Make it 0.5 radians per second. So first I would just compare these two. Okay. So in that case, this is approximately, I would put, how would I do that? 0.05. So 0.05. Right? If I want to do that, I divide this by this one, so it would be like that. And this one would be more, I would probably put a 10 over here. Radians per second, angle in terms of radians, and this is V. And because this will be a large number, right? Any small change over here, a 1% change will affect this much. A 1% change over here would be multiplied by this. So I would somehow start with something like this, just to balance out the units, okay? And then I would start adding things. I would start saying that, okay, maybe the velocity is really important to me. So let's make it like that, okay? And then I might say, well, P is really important, so make it like this. And R, not so important. Phi, not so important, because if I control P, then phi will follow. So maybe the controlling on the phi shouldn't be as harsh as this one here. So I would start with, make these arguments when I start this. You have to remember that this is still, all goes to the performance index. Okay? So it's a numerical optimization problem that's happening here. So when you do that, you have to have those arguments of saying that V should be large, P should be large, R should be large or small, compare them. So which one do you want to see to move over there more is kind of the argument you're trying to make. Okay? So, and of course you still have the controls, right? Plus, in this case del A is only one number, so R times del A square, right? That's also in the integral dt. So how do you choose R? Well, R is in terms of radians, so it should be somewhat comparable to maybe this or that. So I can choose it just 1 or maybe make it 2 and then try. Okay? So these are the arguments. So what do I have here? I have 0.3 currently for the velocity, so the side velocity, which is already quite high, because comparison-wise, P and V velocities, they are quite far apart. And then P, you have here a 1, okay, and then I have a 10. Turns out I do put a lot of emphasis on R. And then I have 5. So that would be for P. So we can arrange this a little differently now. Maybe we can do it the way we want. So let's make it 0.05 for the velocity, okay? And then 0, 0, 0, semicolon, 0, and the second one we said was P. I want to put more emphasis on that one, 3, okay? 0, 0, semicolon, and then you have 0, 0, and then we put a 1 to the R, okay, 0, semicolon, and then 0, 0, 0, and then put I don't know, I put a 5, that's not bad, so put a 5 for the velocities. If you look in literature, that's another thing you can do for your project. Look for papers or books, okay? There are certain ways to find the best values for this. It does a similar thing, similar argument. It takes the largest value, divides by normalizes basically the states and things like that. So you can do that. For R, I have 1, which is fine, okay? So let's use that. And then we can use, finally, LQR. So I had it somewhere here. Boom. So that's it. KSE is equal to LQR ABQRN. Okay, Q is the one that I just used over here. R is the one that I have here. This is the K, feedback gain K now. Okay, and this is the S matrix, remember, from the Riccati equation. Okay, 2 of them, they are now complex. 2 of them went to -5, -6, and 2 of them went to -0.3. So remember when I did the P1 matrix, the place matrix, I made up the eigenvalues where I want to move them. I moved them to -0.1, 0.2, 0.3, 0.35, but I really didn't have an understanding of which states I want to put more emphasis on, right? I just said move the eigenvalues over there. But which states should move less? There was no understanding of that. Now in LQR I have that understanding, and with this weight matrix I use over here, it actually moved the eigenvalues over here, the LQR problem. Moved it over here. And this is quite different from that. Now the eigenvalues move to a place that maybe makes sense in a certain way, because the argument here when you design it is who should move more. Okay. So let's see what happens when I use this new K value. So if I do this, the new K value is this one, and which is already in Simulink, right? I mean, it's already here. Simulink will automatically pick up that K value that is newly calculated. All right? So if I run this, let's see what happens. This is the response. It's not too bad. You see? And this is your phi value. Goes up to here. Step input was 0.2. Okay? So we can increase the input maybe a little bit and see what happens. So this would be the pilot. The pilot would be using this. Okay? Larger input. You still have a nice stable system. Minus 0.15 would be the phi angle, the roll angle. Okay? Another thing you can do is I have a sine wave over here. You know, you can tell the pilot to give a sine wave. The amplitude we can do it 0.3 like we did before, and the frequency 0.5 radians per second. Okay, so you can just remove that and add it to this. Now the pilot will give a cyclic, not a cyclic, that's a helicopter. It will give a lateral control input. Okay, so let's see what happens. 30 seconds. So this is what happened. All right, we can run it a little longer to see what happens, maybe 100 seconds. Say run. So that's it. A lot of oscillation, but the oscillation, you have to remember the input that we are giving is an oscillatory input. Okay, we run it again. So this is the input. This is what the pilot gives in as an input. Does this. Okay, I mean, this, of course. It's a lateral, so it's doing this. And the aircraft responds. This is phi. The aircraft is going sine and doing that. Does it very nicely. Okay, it follows the command here. Let me try to put it over here and see what happens if you give it to the open loop airplane. I keep saying helicopters, I don't know, I'm just used to helicopters. All right, you say run, okay, and see what happens to the open loop. That's what's happening to the open loop. See, you're going up to these 50s and large numbers. What did we over here? What did we have over here? Oh no, this is the phi. This is between -1 and +1. So the side velocity is much less, right, for the same input. So this is how you would kind of design these things. Of course, you can say, well, let's change the Q. Don't make it 0.05, but make it, I don't know, which one should we change? Maybe change the phi. Change the phi to 1. And the P to also 1, and see what happens. K is over here, come back here, run, and you immediately have a new response. And you can check what really happened here, what really changed and what really did change. Now, what I think what I can do is, I can put this file on the website, and you can try it home. But please go and try to understand, get a feel of what is happening here. Okay? Because if you don't do that, you know, we are calculating these gains, and in the exam you will calculate gains, but control design is really getting a feel for what is happening here. Okay, so this is that. Now let me go one more step, and this is here. Let me just move that over here so we have a clear picture. I got that one too. Okay. So this is my new controller. So what do I have? This is the same feedback controller here with the gain here, K. Okay. So what did I do? I just chose one of those, which is phi in this case, right? The last one. Fed it back. This is like a C. So remember that I multiplied this with C and got Y, and then turned it back and multiplied with K. It's that case. What I do here with C is I'm only using the last one. So Y is equal to this, like it's like 0, 0, 0, 1 V P R phi. So that's your C now. So you multiply this with this, so Y is equal to phi. So that's what I did here, right? You take X, you take the fourth one, which is that phi, and then you feed that phi back and compare it with that phi. This is now your tracking problem. Now what you expect now is that you expect that this minus this is the error, multiply it with some gain, and then send it over here. So this loop should somehow make this control, this command, equal to that. So until they are equal, there will be an output coming from here. Okay? So this is now the stabilization loop, and this is now the tracking loop. Okay? So I didn't calculate this number here, so I'm just going to make up these numbers. I think -8 might be too large. I don't know. Since we are not calculating now, this is a little tricky. So the step input here is, let's make it, I don't know, 0.6 radians, the final value. We will start it at time 5 when the system has stabilized. So at t equals 5, the final value here is 0.6 for the step input. But since I'm feeding back this phi, I'm expecting that the phi will somehow converge to this number. There might be a steady state error, I don't know. -4 might not be a good number, I don't know. So we will see. Okay. So what was the number I was trying to get? 0.6. Where did phi go? It went to 0.4. So there's quite a large of steady state error. You see that? The phi was trying to go to 0.6. But it just stopped here. So we have quite a bit of a steady state error. Please see what I'm trying to do? You can put it over here maybe. Put it here and see what the error looks like. Sorry. Okay. So run. So that's the error. You see, this is the error between the actual phi and the commanded phi. That's that error. And you see that error starts large, becomes smaller, but the steady state error continues. It's 0. Sorry. It's very hard to do this on a small screen. See, the steady state error continues to be at 0.15. The stabilization loop is the LQR we just designed. Now I have an outer loop that is trying to track phi. Okay? Now let's see what happens if you increase the outer loop gain to 6, let's say. Let's see if the steady state error will reduce. Maybe a little bit. It came closer, you see. And the steady state error is now closer to 0.1. How about 8? Maybe 8 wasn't the bad answer after all. It comes closer to 0.6. 0.5. 0.5 was the one that I wanted, right? Yeah. No, 0.6. Sorry. So maybe make it even larger then. Well, the steady state error doesn't really go all the way to 0. But it is doing something. If you make it really large, let's see what happens if you make it really large. Make it 50. Now you start oscillating, you see? The steady state error is quite small now. You don't see it here on the screen. Now you can see it. It's 0.6. It's really small. But now you start oscillating and you have these abrupt things and all that. So you don't want to go really too high. Another thing is this assumes still perfect measurement of phi. If there's an error in phi, then you will amplify that error and it will get you into trouble. So a meaningful thing is to really keep -8 over here. Okay, and this is what it looks like. You have a steady state error of 0.1. It behaves kind of nice. It doesn't have this large overshoot. The overshoot is okay. What happens to the rest of the states? Let's look at that. The rest of the states are fine, right? Nothing blows up, nothing. Now, you might say, okay, this is good, and I'm telling you this works fine because the inner loop is nicely stabilized, okay? Let's say for a moment that we don't stabilize the inner loop very well. What happens to that? Okay, so currently the k value is here. Let's say k is equal to 0, 0, 0, 0, which means no feedback. Okay, let's see how this works now. Never tried this. This is what happens if you don't stabilize it. You see? So we would like to still keep this k value that we designed over here. Okay? So this is without, sorry. What happens to the rest? Well, the rest is even worse. I mean, I only look at phi, you see? Phi is, yeah, it seems to go to 0.6. It's oscillating a lot, but look what happens to the rest if you don't stabilize. See, this is the side velocity. It goes to plus minus 80. So it doesn't work very well. But if you do this now with our new k value, okay, you have the steady state error, you have a meaningful phi, but at the same time, look at the other states. Everything else is behaving very nicely, you see, with the stabilized system. So you stabilize and you have this so-called outer loop. Now you can track phi. So what you can do here is, this one, what we do here sometimes is now the pilot is sitting here. The pilot is sitting here, okay? The pilot might be able to give a command to the aircraft saying that let's take the aircraft to 30 degrees of phi, okay? You can either do this in the controller, or you can just connect the pilot stick to this. So the pilot will just do that with the pilot stick, which will which will send a command to the controller saying that move the aircraft to 30 degrees of roll. Then because the controller will try to move the aircraft to 30 degrees of roll, this will give an input of 30 degrees. The aircraft will go to 30 degrees. Go to 60 degrees, the aircraft go to 60 degrees. Okay? So the pilot control will no more be connected to the ailerons. It will be connected to the computer. And the computer will only get the input of 30 degrees, 60 degrees, whatever, 10 degrees. So the pilot will be controlling effectively the roll angle. So the pilot will no more be connected to the ailerons. The aileron is moved by the controller, by the autopilot. The pilot will only do that. And the aircraft will go to that. And this is very typical in a lot of airplanes, including fighter airplanes. The pilot will know if you go to maximum, you will do this. If you do this, you will go to that. If you do this, you will do that. So you don't mess with the ailerons. You know your command is phi. Is there a disturbance? Okay, if there's a disturbance, turbulence, wind, I don't care. This controller will always try to make sure that the aircraft goes to the control input that I give. The ailerons will start doing this. They might be moving a lot. In fact, if you look at the controls, see, this is the command. This is the error. right? This is the error. And this is a step input. Look what happens to U. U is moving, shooting down here and then going up. I would like to see that part. That would be a lot better. No, it's not moving anymore because it's a step input, but I could maybe a good way of looking at this would be to look what comes out of here from the controller, right? This is the controller output. This is the controller output. Of course, it's a step input. It's not doing much, but the controller is helping. See, this is what comes out of the controller. This is not what the pilot is giving. This is the control signal that's been subtracted from what comes out of here. And the pilot doesn't even know. I mean, the pilot is so far away from what's happening here. There are 2 loops before it goes into the actuator over here. Okay? And this is a simple input, really. I mean, I'm just giving a step input. We could be giving, again, a sine wave as before. In MATLAB Simulink, what you can also do is you can connect your joystick to this signal. Instead of this sine wave, you could connect your joystick. And then you can fly, and I do this, and at the same time see on scope how this thing moves. You can do that too. So MATLAB Simulink is quite flexible. In fact, what you can do in MATLAB Simulink is also, you can replace this with a real model, put a picture of an airplane, and then put your joystick over here and then start flying with your controller. This would be something you can do for your project too. Okay? Just go and search for these things in MATLAB Simulink. There's a lot of interesting things. Okay? You understand that? We do that in the lab all the time. Put a little airplane figure that flies and connect your joystick over there and then start flying. And then you can put your model over here. You need a model. It can be linear or nonlinear. Put a linear model, design the controller and see how it flies. And then you will not be controlled. Try controlling this first and then design a controller and then fly this one. And then maybe you like the controller that you designed because it's easier to fly. And if you don't like it, then you are a bad control designer. Okay? All right, so I don't remember what this was, 0.3, 0.5. Okay, so go. Boom. (0.3) plus minus 0.3. Okay? I don't know what this was. Let's see. It was the amplitude was 0.3, frequency was 0.5 radians per second. So this seems to be following it quite nicely. Okay? What you can also do is actually you can connect these 2 signals and plot them on top of each other. I'm not going to do it here, but you can try it at home. So this is the output of the controller. And this is the output. And this is what goes actually into the controls. All right? So, as you realized, I did this by using LQR, the inner loop. The outer loop, I did it by hand. Of course, we can calculate that as well. But what we learned really in class was this one. Let me just remove that. We learned this, right? We have the gain, we have the integrator, right? And then we have the integral gain, and then we have this linear model. Okay? So, of course, once you have the gains over here, we have calculated the gains, it's a little silly for me to make up this number. I don't want to make up this number now because we know how to calculate this in class. Right? What you can do is you can do the following. How do you calculate that? Oh, here. Of course, again, I take the phi value, send it back over here, compare it with this phi value, put an integral, put a gain, and then put it up here. Now, you might say, how are we going to calculate this feedback gain K, right, in conjunction with LQR? Because we never did that. We had just 4 eigenvalues, right? And then we added an eigenvalue for the integral. Remember that? Remember that or not? How did we calculate the integral gain? I gave you 2 desired eigenvalues, or 3, whatever, and you added the 4th one, right? And that was supposed to be far away from everybody else. That's how you design the integral controller. Now, in LQR, I don't give you that. I don't give you eigenvalues. Do I? No. The LQR optimization problem decides for you what the eigenvalues should be. And you need to add the 4th one. So how do you design that? Well, you can do the following. Since we did the LQR is giving you the desired eigenvalues now. It says if you use these optimization weights, then the eigenvalues shall be here, right? Now you can use these desired eigenvalues in the integral problem as the desired eigenvalues. Do you understand that? Understand that or not? Okay, so it will be now the desired eigenvalues are now dictated from the LQR problem. Okay, and you use that as the desired eigenvalues, calculate your integral gains, and those gains will change, of course. Remember, in the integral controller, you cannot first calculate that and then change the gains on the other side. You cannot do that. But since you know these ones now, you can go back and calculate the feedback gains and the integral gain together. Does that make sense? Okay, it's a little bit more involved, but at least you know what you're doing. Okay? And what I want you to do for your project is that you do something meaningful in the integral controller and do something like that. I mean, in terms of the calculations. Okay? So this is something you could do for your project, just like I explained it to you. Right now, I don't have the setup here to do the integral controller in a meaningful way. So I'm just going to take a chance and add a number over here, but I'm very scared that it will actually destabilize the whole system because, as you know, you cannot, as I did on the other side, because on the other side there's no integral, the one I just did, the tracking controller. There I can add numbers because there I'm very safe. You see, it doesn't change the eigenvalue of the inner loop. Here, you remember here, this one? I don't change the eigenvalues of the inner loop when I do this. But here, because of this integral, I'm adding another state to the system because of this integral, and it will correspond to another eigenvalue. And therefore, the gains over here with this integrator, the eigenvalues, I don't know where they go now. Okay, they might go anywhere. So I'm just going to take a chance and add a number over here, but it might, I'm just warning you, it might destabilize the whole system. Okay, what do I have? I have minus 0.1. I'm just taking a chance. I don't know if it's going to work. Well, not too bad. What was the input? The input was 3, so it worked perfect. So I just got lucky. Final value 0.6. I think that was the one we did on the other side, right? Boom. And I have the perfect 0.6. Sorry. Part of the problem is you don't see everything on that screen. Okay. Now you have the perfect response. I'm giving a step input at the 5th second to go to 0.6, and the aircraft really moves nicely to 0.6 and no steady state error. You see? And this is probably what you wanted to see if you wanted to design a controller where you say, okay, the pilot is going to give this input, the aircraft is slowly going to go to that 0.6. Slowly go to that 0.6. So can you do that faster? Can you do that faster? Of course you can. but then you have to, I don't know where the eigenvalues went at this point. You can move the eigenvalues a little bit further in the real axis, or you can say, this phi, I want to move it a lot. So just reduce this 10 to a smaller number, then it will move a lot. Maybe we can immediately try that. I don't know if it will help, but we can immediately try that. So this was my Q, right? Okay. Maybe the phi, we want to leave it a little loose, which means the phi should move faster. Okay, so I can reduce the one in phi. I can even reduce the one in P maybe, so that it moves a lot faster, so it gives a faster response. So in that case, the phi will, but it might now have the potential to overshoot now. Okay, so let's do the LQR. Boom, didn't change anything. The only thing that has changed here is now this K value. See what happens. Boom. I don't know. You see? It did. It went up faster. It overshoots and comes back. Because I told the optimization problem that P and phi can move. Because I made them smaller. These gains are now smaller, which means the movement of P is multiplied with smaller numbers. And therefore, the optimization problem is putting more emphasis on V and R instead of P and phi. So it says P and phi can move. And it did move more. Moving more means that it goes faster. But then it overshoots. Do you see that difference? Want to try it again? Do the other one? I think this was the other one, right? 1, 1, 1. Okay. So LQR, boom, boom, run. That's your phi. It's slower and it doesn't overshoot. Because phi is now not moving too much, because we told the problem, don't move phi too much comparably to the others. Okay? Now, here's what I suggest, really. Take this, I will put this on the web, okay? You'll get it in Metu class. This file, this MATLAB file. Try all these things. That's how you get a feel for it. Otherwise, it's just memorizing just some numbers, okay? But if you master this, if you really understand, you'll become a good controls engineer. You can do a lot of things with this. Here, I'm just controlling phi. Can you imagine that I have another controller that controls now the velocity, the side velocity, maybe the theta, right? And then in your homework, in your project, I put a third loop that is actually controlling another one. Because what you can do is you can put another loop over here. The command will be the velocity. Velocity is commanding theta. And theta is commanding, is giving the input to the actual system with a stabilization loop, so that would be a velocity controller, okay, for an aircraft. So we got a little bit lucky with this, though. I mean, I just made up this number. So this is how much I want to show you. We have something called a PID controller. You might have heard of PID controllers, right? This is proportional, integral, and derivative controller, okay? This is classic control, okay? If you really want to learn PID, you need to take 384, AE483, AE483, okay? However, PID is not any different from what we do. Okay? Everything you can do with PID, you can do over here. There's nothing any different. Let me just give you an example what a PID would look like. So this is what a PID would look like. Now, I have the same steady state. I have the integral over here. Okay? A PID would actually add another gain over here and add a derivative over here and add them all together, all these three. So you take the error, the derivative of the error, multiply it with a number. You take the derivative, you take the integral of the error, goes in here. And you multiply the error with a gain and send it over here. So add it all together. So it will be like, see, if you don't have the integral and the derivative, you just have the gain. It is a tracking controller I designed over here. This would be a P controller because you just have a proportional control. Okay? If you have the integral here, this would be an integral controller. If you have integral and proportional, you have a PI controller. If you had a derivative on top, you would have a PID controller. Okay? Now, I didn't do that too much. You can, of course, do these things. But at the end, the architecture for a PID controller is, again, the same thing. All right? So what you're doing in this class, in PID, you do a similar thing but in a different way. Okay? That's one. Two, PID requires one single input over here. And our integral required one single. The tracking required one single input. Okay? But when we design this one here, I get the full state feedback and send it over here. And this is not PID. You cannot learn this. This is modern control. That's why we call this full state feedback control. You get a lot of numbers over here, send it over here. Okay? So this is you're feeding back the whole state. Here you're sending in one number. Therefore, 384, AE483, classic control is single input, single output system. That's why I was telling it is a single input, single output system, because you need one single input so that you can take the integral, derivative, and proportional and send it over. Okay? But this is full state feedback. So typically what we do in controls problems in aerospace, we would stabilize the system with full state feedback, like in modern control, and then wrap around these loops to control other things, to track things, velocities, angular positions, and so on and so forth. Understood? Okay. So this is all I want to show. Do you have questions, first of all? As I said, I'm going to put this file onto the web with the numbers that I have inside, and you can try. Of course, when you hit run, it will ask you what is the K feedback, and you have to calculate it. You can place it, or you can use LQR, whatever you like to have. Any questions? Yes, please.
So could you show us how to design an observer?
I'm sorry?
Could you show us how to design an observer?
Okay, maybe next time in the next class hour. I think we have 2 more weeks, right? 2 more weeks. Okay, so we have quite some time. The material is almost done. So I can use one of these class hours to show you more, maybe, observers and things like that.
By the way, we have only one week.
Why?
Because it's after the New Year.
So there's no...
No class, there was no class.
Okay, so we make another Wednesday then.
Are the videos or uploaded for the...
That's the person over there. Talk to the camera.
I talked to him, but he said you are responsible.
I'm not responsible. I already emailed
Ah.
the person. Okay?